Hi. I would like to start by thanking the organizers first for having me and giving me this opportunity to present my work. I should also um, give this strong disclaimer that um, whatever I'm going to talk about are my own views, not my company's views. Whatever I'm going to talk about is also published online, so it's public knowledge. Uh, so with that out of my way, so I'm going to talk about similarity learning in financial services. That's a topic that I've been working on for the past a few years since I joined financial industry. And my background is more academic. I come from applied mathematics slash theory of machine learning background. And this is one topic that is very close to my heart. And it's, of course, very well appreciated in parts by the financial industry, but it is still requiring some rigor. And there are so many other applications that I'm also excited about. So let me just start my talk. So first, I'll start with this famous cartoon from Alice in Wonderland. So Alice meets with this Mad Hatter and March Hare, and Mad Hatter asks Alice this interesting puzzle: why is a raven like a writing desk? Essentially, he's asking Alice how to define similarity between a raven and writing desk. And then eventually, of course, in the book, Mad Hatter himself says that there was no answer really. It was a nonsensical puzzle. But then afterwards, of course, people were very curious about this puzzle, and people started attempting to give an answer by themselves. So some of the answers that I found very interesting and are available on the web in some forums. So one answer is because Edgar Allan Poe famously wrote on Raven, the famous poem Raven, and then he also wrote on writing desk, obviously. So that's probably why they are similar. Another interesting answer I found was because outstanding bills are found on both of them. Another one is because a writing desk is a rest for pens, and a raven is a pest for wrens. And then Lewis Carroll himself, eventually, when asked by some journalists, gave his answer, not in the same book, of course, but elsewhere. So he said, because it can produce a few notes, though they are very flat, and it is never put with the wrong end in front. And of course, Carroll being Carroll, he also misspell never, so that it reads Raven backwards. So this is one very interesting puzzle about similarity, in my opinion. Similarity is one of the fundamental cognition skills. So recognizing similarities in the world between two objects, between multiple objects, and then dissimilarities, of course. That is one of the fundamental cognition ability for the humans, as well as many living organisms. It is also an important survival skill, and psychologists and evolutionary biologists have been studying how people recognize similar objects and dissimilar objects, and how the evolutionary mechanism helps us developing this skill, and why is it even necessary in the first place, and so on. So this is one example from the art. The on the left, it's famous Mona Lisa painting, and on the right, self-portrait with monkey. by a Mexican painter, Frida Kahlo. So people also discuss in scholarly literature similarities and differences between these two paintings. We come closer to our world. So what is the actual question that I'm interested in here when I say I'm interested in similarity? So first question is, given an object or a product, what are other similar products? Okay. Can I identify other similar products if you give me one particular product or an object? And you can also ask the same question, but in a different way. If you give me two objects, can I come up with some quantitative measure of similarities or dissimilarities to compare these two objects? It's very frequently arising problem in most business areas. And once I start giving you examples, you'll realize that, of course, these all are similarity examples, and they are very day-to-day examples. So one is Amazon recommendation system. If you are searching some item on Amazon, it will start recommending you some similar items. Netflix recommendation for similar movies is a classic example of recommendation system, and as well as essentially similarity. Zillow's estimate of house prices is also based on similar houses. So if you are trying to find or estimate price of a house, and then Zillow basically tries to identify top 10 or top 20 most similar houses. And here, by similarity, we mean the number of, in terms of the number of bedrooms, dwelling, lot size, crime rate in the specific area, school district rating, and so on. So using all these features, you identify top 10 or top 10, 20 most similar houses. And then the mean or median of prices of those houses would be a good estimate for the price of the house that you are looking at. Spotify's song, podcast, artist recommendation system, that's also similarity engine. Face recognition on Facebook, or even on your cell phone to unlock your screen. That's also similarity, basically. In most of the NLP algorithms these days, Word2Vec, BERT, GPT, GPT 2, 3, and so on, underlying computation is essentially semantic similarity among words. Facebook friendship recommendation system, that's also an example of similarity. It identifies similar individuals with, say, similar interests, or maybe who also have similar friends as you. So that's also another example. There are so many different examples that I can get going on this. But let's come even closer to finance. So what are the applications of similarity in finance? And I started working on this similarity 3-4 years ago, and I started realizing that there were so many applications of similarity, starting from similarities between assets. And again, a very popular example might be illiquid assets. When you are trying to trade an asset, for example, a corporate bond, with a more liquid asset, so more liquid corporate bond. It's called trading liquid substitutes. So there we have similarity at play. It's one of the most interesting applications of similarity. Mutual fund or ETF similarity is also yet another application. And once you have good similarity tool for mutual funds or ETFs. You can start using it to compute portfolio diversification, to create alternative portfolio than the one that you already have, and you want to replace it by your homegrown product, for example. You can also use the similarity tool for sales and marketing purposes. So if your salesperson goes to an end investor and he sees that uh, the end investor has some competitors' products, the salesperson will run the similarity tool and will start giving similar homegrown products as options to the end investor. Tax loss harvesting is also yet another application. So at the end of a tax season, at least in the US, it is sometimes good to realize loss by selling some mutual funds or ETFs, and then immediately buy similar ETFs or mutual funds to retain your risk return profile. It's called tax loss harvesting. And again, similarity of mutual funds and ETFs can be extremely useful here. Algorithmic trading is also one of the most used form of similarity here. So pair trading or arbitrage and so on, they go by different names. But in short, algorithmic trading or even relative values, they all are nothing but similarities. Most of the times they are similarities based on correlations, but most of the algorithms in finance still rely on correlation based similarities. But in this talk, I want to go beyond correlations. Going beyond correlations, and by that I mean computing similarities based on some attributes of the particular financial object. If it is, say, bonds, then I want to identify similarity based on number of features such as rating of the bond and which industry or sector the bond falls in, or maturity date of the bond, coupon rate, and so on. So that is going beyond correlations. But then it is also much more tricky than computing correlations, because then you have so many features and hence high dimensional problem. And most of the times the data set in finance is also very noisy. So it's much more interesting problem suddenly to compute similarity in this high dimensional, very noisy data. In this talk, I'll focus mostly on similarity among corporate bonds, but these methodologies that I'm going to talk about can be extended to any other asset class or any other financial object in general. And what are the applications of similarity for corporate bonds? So first, corporate bond market is very diverse. Securities are traded in varying volume and frequencies. Many illiquid bonds are there, and sometimes you want to buy that so that you can reduce your tracking error for an index fund, or maybe maximize the returns for an active fund. But that particular bond is not available to trade in the market. So if you are a trader, you might want to then identify some similar bonds which are more liquid, meaning the trader would like to identify liquid substitutes for trading and investment purposes, so that they can also reduce transaction costs and maybe improve fill rates, reduce negotiation cycle between traders and portfolio managers, and so on. So that's one big motivation to identify similar corporate bonds. And it's also the same arguments are valid up to a certain extent for any other illiquid assets. Uh, so these are some uh, uh, important reasons to come up with a system that that identifies similar corporate bonds once you enter a QSIP for a specific corporate bond that you are trying to trade. Okay, so that's basically the goal of a similarity um, tool for corporate bonds. But how do you identify similarity? And first of all, how do you define similarity? So I keep talking about similarity, but first I would like to define what similarity is. So imagine we have some n number of variables, and then so n number of variables, meaning the variables might be, say, bond rating and maturity date, coupon rate, industry, sector, and so on. There might be, say, 25 features or 25 variables in the traditional language. Then bond is nothing but a point in this n-dimensional space. Okay, so each point is a potential bond, or the rather, each bond is nothing but a point in this n-dimensional space. Now, two bonds are similar if the two data points corresponding to these two bonds in this n-dimensional space are close. Okay, so I am defining similarity now as closeness between two data points in this n-dimensional space. But then you can again ask what I mean by close. This is still a word in English. What does it actually mean mathematically? So closeness means distance, mathematically speaking. So distance between the two data points in n-dimensional space is a quantitative measure of closeness. So if the distance is small, then I call these two data points close. And if the distance is large, then the two data points are far. But then what is the specific expression for the distance? How do we define distance even more rigorously? And usually people comes up with the answer Euclidean distance, of course. The Euclidean distance is the most popular distance metric. People learn this in schools and then just retain that for the rest of their lives. And it's simply written as this formula. So distance between x and y is square root of sum of squares of the elements of this x and y vectors. Okay, so it's a famous formula for Euclidean distance. But is it the only option? Is the Euclidean distance the only option to define distance or closeness between pair of data points in an n-dimensional space? And not necessary. So I can just give you two simple examples which will give you some intuition why Euclidean distance is not always a good distance metric, even in real life examples. So on the left, you are seeing the map of Manhattan streets. So if you want to go from point start to point end, the red line is the Euclidean distance between these two data points. But you cannot walk in that straight line, the red line, because then you will be walking through the buildings. which is not always possible. You might not be allowed to go inside certain buildings and so on. So Euclidean distance is not a good distance metric to walk within Manhattan. Rather, you'd take this blue line path, which is uh, uh, which is a good distance, or which is a good path to go from start to end. On the right, you are seeing the Earth, and you want to travel from, say, Sydney, Australia to New Delhi, India. And again, you cannot just compute Euclidean distance to figure out the distance between these two cities, because then you are assuming that you can penetrate the Earth. Rather, you are supposed to be on the surface of the Earth. And hence, the distance metric has to take into account the curvature of the Earth. And it's called Haber-Sein distance in the cartography literature. So again, Euclidean distance is not a good distance metric here either. So for a given data set, what I'm arguing is that you should identify a good distance metric that takes into account the shape of the data manifold. But in high dimensional space, or if you have, say, 20, 25 dimensional data, or 20, 25 number of variables, you cannot even visualize how the data manifold looks like. So how will you pick a good distance metric? Most of the academic literature on similarities in finance and economics that I've been reading, they almost always either explicitly or even implicitly focus on Euclidean distance. They just assume that Euclidean distance is the right metric. And doesn't matter what the shape of the data manifold is. But it's very important to pick a correct distance metric for your own given data set. It's a very well-known fact in many other areas of science and engineering. For example, in physics, importance of distance metric is always there, right from first chapter of any technical book. But in many other areas, the importance is not very emphasized. So here is the proposed idea. So of course, you cannot visualize the data manifold in most cases, especially if the dimension is more than 2 or 3 at least. So how will you even come up with a good distance metric? So here is the proposed idea in this talk and in this work. Instead of us choosing a specific distance metric, such as Euclidean distance or Chebyshev distance or Minkowski distance and so on, what we are proposing here is to learn the distance metric from the given data set. So rather than you guessing distance metric, you just learn the distance metric from the data. In machine learning, there is a niche area which does exactly this, which is learning distance metric from the given data. And it is called distance metric learning, or sometimes it is simply called metric learning. And it is a niche area, and of course, people have been studying this for many years now, but still it has not penetrated the economics and finance literature yet. So let me give at least some glimpse of what this distance metric would look like. So there are many methodologies to learn distance metric in machine learning. The first one is just crude method, so trial and error. You might have some list of predefined distance metrics such as Euclidean and Manhattan and Chebyshev and P-Minkowski and so on. And then for your given data, you choose some specific metric that you want to optimize. And then you keep changing this distance metrics, meaning that you treat distance metric as a hyperparameter. And you tune this hyperparameter such that you optimize the chosen metric. So that's basically trial and error, or maybe more sophisticated way of saying it is that you have to do hyperparameter tuning to identify a good distance metric out of the ones out of the list, okay, predefined list. But there is better way to do that, of course. So it's called supervised distance metric learning. So here you do not pose this problem of learning distance metric as an unsupervised problem. You pose this problem as a supervised problem, first of all. So that is an important point. For supervised distance metric learning, you pose the machine learning problem as a supervised problem, either regression or classification. And hence, you need to have some sort of labels for your data. And once you learn this supervised classification or regression task using some good machine learning algorithm, you work backwards to identify the distance metric which would have made these target labels possible. And I'll show you what exactly I mean by all these abstract ideas. But this is a basic philosophy. So you start with some labels, learn this supervised classification or regression problem using some machine learning algorithm, and then work backwards to identify the distance metric from the algorithm. So, and we are going to use this supervised distance metric learning here in this work, not trial and error. So here is how the specific distance metric learning method that we devised works. And this methodology is based on tree-based method. And by tree-based methods, I mean, it can be decision tree, or it can also be extended to random forest, gradient boosting, extreme trees, light GBM, cat boost, and so on. So, in this specific methodology, at least a preliminary version of this methodology was already proposed by Leo Bremen himself. He was a creator of random forest, and he had already proposed this idea in 2002 with Adele Cutler. But we refined this idea, and we tailor-made it to use it for corporate bonds. Okay, so here is the two-step process for any tree-based method. So in step one, as I said in the previous slide, you learn a supervised learning task using a tree-based method. For example, decision tree to start with. And I'll just show you how decision tree would work, and then I'll go to random forest. But let's say you train your algorithm, your decision tree algorithm, on your given data. And what do we mean by data here? So for the corporate bonds case, our input features would be all the bond attributes that I mentioned, ratings and time to maturity and industry and sector and coupon rates and so on. So all these are our input features. And of course, you can imagine sector, industry, all those categorical variables, one hot encoded or some other encoding, and other variables are just numerical variables. So all these are input variables. The target variable may be, say, yield to maturity or options adjusted spread or beta spread and so on. And for the purpose of this talk, we are going to use just a yield to maturity as our target variable. So in the first step, we use, say, decision tree here to learn the mapping between these input variables and the target variable and learn the supervised regression task. And it is regression task because yield to maturity is a real number. And then in step 2, so once you have a well-trained algorithm, well-trained decision tree in this case, you compute similarity as follows. So for each pair of data points, in this case, each pair of bonds, you pass them through the trained decision tree. And the trained decision tree might look like this. So feature 2 is greater than 32, and then you have a split. And then on the left, you have feature 2 greater than 15, yes or no, and then you cascade to the next level and so on. So this might be your trained decision tree, say, and then you pass each of the pair of data points through this trained decision tree. And then you record where each of the data points ended up. So for example, in this figure, data point P1 and P2, they ended up in the same leaf node. So if that happens, if 2 data points fall in the same leaf node, then I call these 2 data points similar. And if 2 data points, for example, P3 and P4, they ended up being in 2 different leaf nodes, then I call them dissimilar. So I do this for all the data points, and I then get all this similar versus dissimilar labels for each pair. And that's basically it. So then I have similarity computation done. So train a decision tree and then compute similar or dissimilar. And the similarity score between these 2 data points is either 0 or 1. If it is 0, then it means that these 2 data points fell in 2 different leaf nodes. If similarity score is 1, then it means that P1 and P2 fell in the same leaf node. Okay. So if it is just a 1 decision tree, then your similarity score can be just 0 or 1. And remember, the distance is nothing but 1 minus similarity. Okay, so once you have similarity computed from this decision tree, you automatically get the distance out of it by just doing 1 minus similarity. So that's just one decision tree, but more interesting is random forest or any other ensemble method. So if you have gradient boosting or cat boost and so on, where you have multiple trees. So let me focus on random forest. So let's say you have 3 trees generated by this random forest algorithm. Then you again pass pairs of data points through each of the trees. So for example, P1 and P2, they fell in the same leaf node in the first tree. Once that happens, you say that similarity score for this pair for the first tree is 1. Okay. Then for the second tree, P1 and P2 ended up being in different leaf nodes. So then the similarity score is 0 for this particular tree. In the third tree as well, P1 and P2 fell in two different leaf nodes, and hence again similarity score is 0. Once you have similarity scores for each tree for the given pair, then you just aggregate them. So basically average the similarity scores. So here the similarity between P1 and P2 is 1 plus 0 plus 0 divided by 3, which is 0.33. So similarity between P1 and P2 is 0.33, and distance is 1 minus 0.33, so 0.66. Similarly, for say another pair of data points, say P3 and P4, they both pair in the same leaf node in tree 1, tree 2, and tree 3. So then the similarity score was 1, 1, 1 for each of the trees. So the total similarity score, the aggregate similarity score is 1 plus 1 plus 1 divided by 3. So similarity is 1. And the distance is 0. Okay. So that's how you compute similarity for each pair of data points or each pair of corporate bonds in our case. Of course, this is the method that I described to compute similarity and or distance from a tree-based method. But you might still not believe me that tree-based methods might also be viewed as distance metric learning methods. So let me at least give you some intuition. I will not go through the math, but what is tree-based method actually doing? So let's say you have this just two features and data points are sprinkled in this way on the figure upper left. And then you train a decision tree, just a single decision tree for the illustration purposes. What it does is it partitions the two-dimensional feature space such that it maximizes the chosen criterion. In this case, the chosen criterion was the mean square error. So for each split, it tried to maximize or minimize rather the mean square error. And hence the left bottom figure is showing the partitions of on this two-dimensional feature space. Once you have these partitions, decision tree spits out output based on which partition your new data point fell in. So for example, here is your test point X, and it fell in this partition C3. So decision tree will just say that the average of Y variable or the output variable for all the 4 data points which are already in that partition would be a good prediction for the new data point. In other words, it is doing more or less the same thing as k nearest neighbor would be doing. So once you have a new data point, k nearest neighbor will just identify k number of nearest neighbors, in this case 4 in this partition C3. And then it will just spit out the average of the Y variable or all the nearest neighbors. So that's essentially what decision tree is also doing, except that k, the number of nearest neighbors, might change from partition to partition. So for example, in C3, there are 4 nearest neighbors. In C4, again, 4 nearest neighbors, but in partition C2, there are only 2 data points, so 2 nearest neighbors. In C5, there are 3 data points, so it's 3 nearest neighbor. So in short, you can view decision tree and more generally random forest, or actually even more generally a tree-based method, as an adaptive nearest neighbor method. It adaptively picks the number of nearest neighbors to be able to correctly predict the target variable. Uh, it was very interesting paper by Lin and Jion in 2004. They rigorously proved that random forest could be viewed as an adaptive nearest neighbor method. And in other words, decision tree or random forest can also be viewed as a distance metric learning, because it is learning the distance metric for different distance metric for different partitions. Okay, so I'll just leave it at that. It's again beautiful math underlying all these figures. You might want to check out this paper and our papers where we are also discussing these aspects more. But I'll just move on. So um, compared to the traditional distance metric learning methods, there are so many advantages for tree-based methods. But if tree-based methods are used for distance metric learning, there are so many advantages. For example, the input variables or even the output variables can be numerical or categorical for tree-based methods for distance metric learning. So most of the traditional distance metric learning methods are based on Mahalanobis distance metric, and they most of the times require the variables to be numerical. But here, random forest, for example, does not require you to have only numerical variables. If you have categorical variables, random forest is fine. Random forest also does not require much reprocessing of the variables. For example, you don't have to necessarily do any scaling of the data, no standardization, and so on. If you have missing values, cart algorithm, for example, is also fine. It can just naturally take care of missing values, and so you're all good there. Tree-based methods are scalable to large data sets. Of course, not as scalable as deep learning, but mid-size data sets, random forest is fine. No need to do dimensionality reduction. So you can just input raw data to random forest and it is fine. You don't have to first do PCA and then use these algorithms. So you also do not need any pairwise labels, unlike many of the traditional distance metric learning methods. So in traditional distance metric learning methods, you might be required to have pairwise labels, meaning that for each pair, you might need label far or close. So here you do not need those kind of labels. You just need output labels, but not pairwise labels. Most interestingly, random forest based distance metric learning method learns local distance metric as opposed to global distance metric. So meaning that sometimes your data manifold might be flat in certain region, and then very wiggly in another region, and then maybe spherical in another region, and so on. So you might want to learn distance metrics which are valid locally. You should not assume that one distance metric will just serve the purpose of doing similarity for the whole manifold. So meaning that you should learn local distance metric as opposed to global distance metric. And tree-based methods do the same. So they learn local distance metric. In addition, tree-based methods are at a nice sweet spot between simplistic methods and extremely complex black box models. Random forest is, of course, not completely white box method, but you can still do many things such as feature importance and and shapely and so on. So it's a nice sweet spot between these two extremes. So coming back to our corporate bonds example, we use this distance metric learning method based on trees, based on random forest to be more specific, on this corporate bonds data. So there were some 10,000 corporate bonds, and then the target variable was yield to maturity. And then we used all these input features: coupon, frequency, duration, country, days to maturity, age, industry, amount issued, amount outstanding, bond rating, and so on. And the evolution metric for training random forest was RMSE. And we also use MAP, by the way. So the goal was mostly liquid substitute identification. And but I'll not go into too much detail there. I just want to emphasize the methodology and some of the preliminary results here. And typical train test, split, and cross-validation, and so on. And then here are some of the results. So first, how well we train random forest itself on this data. So RMSE was 0.21, and then for five-fold cross-validation for train, and then for test split, RMSE was 0.51. And similarly, we had 0.08 and 0.15 MAP for train and test. So once we train this random forest, we extracted the similarity based on the computation that I just described. So aggregation of similarity based on the number of times two data points fall in the same leaf node. But then how can I claim that this particular distance metric is better than some of the other traditional distance metrics, such as Euclidean distance and Goer distance? So what I did was I used KNN, but now we use KNN with 4 different distance metrics. One was Euclidean distance. So just take raw data and compute the Euclidean distance and compute KNN based on Euclidean distance. And then on the x-axis, I'm running K from 2 to 25. And on the y-axis, I'm plotting the performance of KNN, where the target variable is the same, the yield to maturity. So in the first figure, we have Euclidean distance, and it is compared against random forest accuracy for train and test both. In the second one, I'm also doing the same thing, but now with Goer distance, meaning K nearest neighbor, but with Goer distance. Goer distance is one of the distance metrics that takes into account numerical as well as categorical variables. And then the third figure is KNN, but now with proximity or the random forest-based similarity distance metric. So still KNN, but now my distance metric is coming from random forest. And the fourth one is again KNN with similar distance metric coming from random forest, but in a very specific way. So instead of computing distance metric or similarity based on all the data, I'm computing distance metric based on just the out of bag data. So I'm comparing all these 4 distance metrics, and I immediately observed that the distance metric that I learned from the random forest, both from all the data and from out of bag data, they outperformed the Euclidean distance and Goer distance. So uh, that's basically my metric of goodness, metric to evaluate the distance metrics. And in fact, this particular um, evaluation metric to evaluate distance metrics is also one of our innovations, small innovations in our paper. So I would strongly recommend you to read our papers to see more details on this work. But in conclusion, here, similarity learning is one of the most interesting areas in machine learning, with many applications in financial services. Using correct distance metric for your given data is extremely crucial. No need to use Euclidean distance immediately. It might not be an appropriate metric for your data. Supervised similarity learning is very rigorous way to define and learn similarity rather than unsupervised methods such as clustering or clustering with arbitrary distance metric. In this work, we proposed using tree-based methodology, and to the best of our knowledge, this is first ever application of tree-based method for distance metric learning in financial services. And these are some of our papers. We have been publishing frequently on the topic of similarity. And we are publishing on similarity for corporate bonds, mutual funds, and then also similarity based on NLP, similarity of investors. That's also another interesting area you might want to look into. So with that, I'll stop here. And again, thanks very much for having me here, and hope you enjoy the rest of the conference.